Hey everybody, this is a special supplementary video production for those who are looking to improve their skill and their speed and efficiency at solving stoichiometry problems. This is for you, and I hope it helps. And we'll focus on the method of problem solving that I've tried to get you all to follow since the beginning, and that's the unit conversion method. And that's where we take whatever the units are that we're given with the amount of the chemical, the amount of substance that's given in the problem, and we just try to keep everything the same by using conversion factors that are equal to 1 and change the amount of substance from the units and the chemical that is given to the units and the particular substance that's asked for. So let's look at the things that we need to do to be able to solve these problems. You have to have a balanced chemical equation first of all, and most of the time the chemical equation, the balanced chemical equation, is given, but not all the time. So you may be asked to balance some equations again, and the reason we need the balanced chemical equations is because we need the mole to mole ratios of the two different substances. We need to take that balanced chemical equation and use the coefficients to figure out the ratio of the moles that we are asked for to moles that of the given substance, so we can use that ratio to cancel out the substance that we're given and replace it with the substance they're asking for. You have to have the correct formulas, and I saw last week a lot of mistakes that people made by putting the wrong formulas in for the name of a chemical, or for not correctly identifying the formula if they're given the name in the question. So you need to be able to do that, and to accomplish that you're always going to need your periodic table to identify the symbols and the element names, and you're going to need the list of polyatomic ions that I asked you to remember and to print out a long time ago, and some of you still have not. So, well, I guess that's what you want. In addition to the polyatomic ions, I have recently added a list of 3 strong acids that you need to know the names and formulas for. That is hydrochloric acid, which is HCl, nitric acid, which is HNO3 with the nitrate ion, and sulfuric acid, which is H2SO4 with the sulfate ion. Those 3 acids are the 3 most common strong acids that you get in chemistry classes and labs and the problems that you're going to see for stoichiometry. So you need to be familiar with those formulas and the names. You need to be able to calculate molar masses, and this is again something we've done for a long time. This is not new to this unit. Look at the periodic table, use the atomic masses of the different elements, multiply those by the numbers of atoms of each element in the formula, and then add everything up to get the molar mass of the whole compound. You do need some patience, and you need some just flat-out effort, some perseverance to work through enough practice problems to get your skill up to a level where you can do this quickly and efficiently. Some people are good at it pretty quick. Most people are not. It's tough, and you need practice to get good at it. The steps that I'm going to ask you to follow, and that I have asked you to follow from the very beginning. The first step is to identify the given amount of stuff. So there is going to be something in the question where they say you have 1.4 moles of oxygen gas, or 3.7 grams of something, or you have 15 liters of a gas, or occasionally, and this will become rarer as we move on through the year, you'll be given particles. You have 4 times 10 to the 22nd molecules, for example. But that kind of problem gets less and less common as we move forward because we don't really count atoms and molecules like that very often. Grams and liters and moles are more important. So you have to identify what you're given. So reading the question carefully should identify that given amount of substance. And you need to be sure that you distinguish that from, for example, a density, which is grams per liter or grams per cubic centimeter for a solid. And that's a conversion factor itself. Or you might be given a molar mass, which is grams per mole. And again, that's a conversion factor that would help you get from one thing to another. So you're looking for a straightforward measurement of matter, number of moles or a number of grams, so forth. If you have that given amount of substance as moles, then you are ready to do mole-to-mole conversion to find out how much of the wanted substance that you have. But if it's anything other than moles, then you're going to need to do a conversion to take the grams, for example, that you're given and change it to moles, or to change the liters of gas at STP to moles or particles. And you do that using those three conversion factors, again, that you've seen since the first weeks of class. Grams per mole is molar mass. Liters of gas at STP per mole is 22.4 liters per mole. And then the particles is Avogadro's number per mole. Once you've converted your given substance to moles, if need be, then you do the mole-to-mole ratio from the balanced equation to change the moles of the given to the moles of the desired substance. And you would do that by using the coefficient from the balanced equation and writing the correct number of moles of desired substance using the coefficient over the moles of the given. Again, using the coefficient, not by the calculated amount of moles. And then that will allow you to convert from the given amount to the desired substance. And then the last step, if needed, if the question asks you for moles of the substance, then you're already done after this step. But if they ask you for liters or particles or grams, then you need to do another conversion, which is essentially the inverse of that conversion, which is number 1 on the slide. Here's the roadmap to success that I pointed out is in Dropbox. This document is, and I think for some of you it would be very valuable to work through some of these practice problems with this little handout sitting in front of you. The steps are given to you there. The different conversions that you need are also given, and this is going to help you solve 90% of the stoichiometry problems that you're going to be given from here on out. So a copy of this at your side may be helpful when you're working on these problems, and something like this on your study sheet may be helpful on the test. So let's take a look at some practice problems looking at different possible styles of question, different tasks you may be asked to do. This first question says, how many moles? So I'm going to stop right there. It says, how many moles? So I know they're asking for moles. Are produced when 12.0 moles of KClO3, that's potassium chlorate. Now I know the given. 12.0 moles of KClO3. When that compound decomposes, the balanced equation is given. You can tell it's decomposition because there's only one reactant. And why is the 3 on the other side of the S? Well, that 3 should be here, shouldn't it? Not there. And I missed a typo there. Maybe I fixed it on the next slide. Let's see. No, it's still missed. So, KClO3. Anyway, so we have our given amount of substance, which is the 12 moles of potassium chlorate, KClO3, and it's asking how many moles of oxygen are produced. I've highlighted the important mole-to-mole ratio from the balanced chemical equation, and the first step is to identify what kind of problem it is. Well, we've got the moles of given, so we're going to start there on the roadmap. And they ask for moles, so, well, this is going to be a one-step solution, isn't it? And there is the way the calculation would look. We have our 12 moles of given. We are trying to get to the moles of oxygen, so we put that on the top. We put the moles of KClO3 in the denominator. That will cancel with the moles in our given, and we do the multiplication, 12 times 3, divided by the product of all the denominators. In this case, we just got 2 down there. So 12.3 is 36 divided by 2, 18 moles. And this is a simple kind of stoichiometry problem, the simplest, in fact, but you'll see them relatively often. And don't be thrown if you have the moles to begin with. It makes your life easier because you only have one step. Next question is another style. Let's take a look at what the words tell us we need to do. The first 3 words very often are going to tell you what you need to find. In this case, how many grams? So we know we are looking for grams of sodium oxide, Na2O. So we're looking for the grams of this substance, and I'm going to circle that the way I do on these kinds of problems and write G next to that. I have no coefficient, so that's the understood 1, remember. And then we are looking for the grams of sodium oxide. What are they giving us? That this amount of sodium oxide required to produce 1.6 moles of sodium hydroxide. So this is the other substance, and this is the given amount. We have 1.60 moles of sodium hydroxide. So we're starting with moles, and they want us to go to grams. What does that look like for us when we map it out? Well, the moles are given again, so we know where we're starting on our little road map. They're asking for mass in grams, so we have to go down to the bottom right there. The first step is going to be change the moles of given to the moles of the stuff that they're asking for, and then the second step is going to be to convert that molar amount of the desired substance to grams using the molar mass over moles conversion factor. And when we do the math, it looks like this. We have the 2-to-1 ratio. Whoa, back up there, son. We get the 2-to-1 ratio from the balanced equation. We write our moles of sodium hydroxide, the given amount. We cancel out the moles of sodium hydroxide using the mole-to-mole ratio from the balanced equation. So there's the 2 and 1 from here and here. And now we have moles of sodium oxide, but the question asks for grams. So we use the molar mass of sodium oxide, 62.0. And that's going to cancel our moles and get us to the correct units for our answer, 49.6 grams. Peace. Anytime you want to go back and take a look at a problem again, I'm going to try to zip through these last couple of examples, but go back as much as you need. Pause things and write down notes. Take your time. That's what's good about the video format. The next one, the reactions of cell respiration are summarized by the balanced equation down here. And it says if a person consumes 1,000 liters of oxygen at STP, that volume measured at STP, so we know we've got an important bit of information there. If a person consumes 1,000 liters of oxygen, well, I'm not sure yet, but that certainly looks like that's the given amount of stuff because it's a simple measurement of matter. If a person consumes that much, how many moles of glucose? So how many moles of glucose? That is what we are looking for. Glucose is C6H12O6, so we know we are looking for moles of this stuff, and they have given us the 1,000 liters of oxygen gas. So we've got where we're starting and where we need to go. Let's map it out. volume of a gas at STP, 1,000 liters of oxygen is our given. And we're trying to get to moles, so we're going to go a straight line across the little diagram. First, converting the volume of gas to moles of oxygen, and then using the correct coefficients from the balanced equation to get us to the moles of glucose. So when we do the math, we have our given amount of substance to begin with. We know the first thing we're going to do is write liters of oxygen in the denominator of the first conversion factor. That's the only way we can change out of our given amount of substance. And we use that molar ratio to change to moles of oxygen. Once we have the oxygen amount in moles, then we can use our balanced equation and do the stoichiometric step mole to mole conversion. In this case, the 6 moles of oxygen from the coefficient in the equation to every 1 mole of glucose. No 1 there, but it's understood. So now we've canceled moles of oxygen, and we get moles of C6H12O6, that is a glucose, and that's what they asked us for. So that must be the correct answer. I could have calculated something wrong here the other day, but I think I got all the numbers right. Next one, grams to liters. Look at the words, and again, look for key words to identify what's the given and what is the desired substance. What are they asking for? This one says when 120 grams of ammonia reacts. So we have 120 grams of a substance given. That is the stuff that we're going to start our calculation with, right? It reacts as shown in the equation above. How many liters of oxygen? And again, the words are almost always going to give you a straightforward, hopefully, a straightforward interpretation of what is given and what is desired. What are you looking for? So again, let's take a look at our roadmap. They said when 20 liters of ammonia reacts. So we're starting out, 120 grams of ammonia reacts. So we're starting off with that amount. And so down in our graphic, that is down here, our mass of substance that's given. And it's asking for how many liters of oxygen at STP. So we're looking for volume at STP. Yeah. So we're going to have to follow this path, and then to here, and then to there, right, to get to our answer. And that's what the math looks like when we do it in the way that I'm hoping you're going to do it. We are given grams of ammonia, so we know we're writing grams of NH3 down here in the first conversion factor. That is the molar mass of ammonia. So now we know the moles of NH3. We want to know oxygen, so we use the 5:4 ratio from the balanced equation to cancel our moles of ammonia and change to the desired substance. And then the final step is going to change those units of moles to the units that they want, which is liters. And that's the molar volume of all gases at STP, 22.4 liters. And there's your final answer. Well, thank you very much. Well. You're so generous and kind. The baby there may be your reaction to doing more practice. But I think it's good to do more practice. I really do. And so here's some more practice problems. Most of these are on the stoichiometry practice problems worksheet that I told you about. It's in Dropbox, so you can see the answers to those. But if you don't have those handy, then you can go ahead and get started doing some of this practice. And again, go back in the video. I worked through not every single possibility, not every single permutation of a stoichiometry problem, but hopefully giving you an idea how to use that roadmap. And whatever you're given, whatever they ask for, you can figure out the correct path to do that. I'll see you guys soon. Bye.